Hey everybody, this is George Ogilvy, and this is my Lab 2 motion of a falling object. In this lab, we conducted an experiment on dropping a ball falling through the air from rest with drag. And we used a tracker to collect the data and analyzed the model of motion. And then, after that, we computed two models on closure, and one was with drag and then one was without drag. The main physics principles used was momentum and Newton's second law. The momentum formula used was F net, which is change of momentum over change of time, constant acceleration, which is negative 9.8, and then force equals mass times acceleration, which is part of Newton's second law. And then the process demonstrated the force of gravity on a falling object. The system includes the spike ball being dropped from rest and the surrounding forces on the ball, which is the drag force. Here you can see I include the little image of the experiment being executed through the tracker app, and you can see the graph of the position versus time, as well as the time versus position. Here's a larger image of the graph created through the tracker app of y position versus time, and as you can see, it starts off and then accelerates more and more as it gets closer to the ground. Here's an image of the GlowStrip code. On the left we have the code with no drag, and then on the right we have the code with drag. With no drag, the position updates with g equals no t, and because there's no drag, that's the only force acting on it. And then with drag, you see use the F net formula, and then to represent drag, you use ball velocity y squared, and then you combine that with the force of gravity. And you do that to find the object moving with drag. Here we can see the observed position versus time that I made through Excel. And these are using the values we use from the tracker app. And then here, you can see the two line plots that I made using Excel. One represents the GlowStrip code computed representing no drag, and the other one is computed using drag. And when there's no drag, the object falls faster, and when there is drag, it slowly reaches F net is equal to 0. We're going to talk about some of the sources of error. The biggest one here is the tracker app. Of course, you can't get it 100%, and you have to manually click the center mass of the ball for each individual frame, so you can't get that 100% accurate. And then the other one is the drag force could be inaccurate. The drag force in the GlowStrip code, we use the velocity squared, and that's very different than the drag force formula we used in class. What does this mean? We have to answer which model represents terminal velocity. And so terminal velocity is seen as the drag force model computed, and we went back to the GlowStrip code to show the velocity versus time graph. And as you can see to the right, the velocity slowly approaches a constant velocity because the drag force slowly increases. And then at force approaches 0. And then the what if the object was thrown downwards? The object was initially thrown downward, there wouldn't be a difference in the terminal velocity because it would be the same as it began from rest. If the terminal velocity was thrown down, it would be the same if it came from rest. In conclusion, the drag force caused an object to fall exponentially slower. The model can be seen through the tracker app. Shows the